Okay, so we'll get started. I mean, I know we took a break, and also, by the way, today is the submission for assignment 4. So let me do a couple of logistical things, and then we'll get into jump back right into where we were about generative models and so on. So, so we are here. Okay, so 28th. So this is the last, I guess, lecture in March. So today assignment 4 is due. I think you guys have already gotten hang of the assignments. I think they have similar patterns, given assignment 1, 2, and 3. But if there are some questions, I hope you've reached out to folks. If not, still reach out to me or the TA. So it's basically the end of today is the submission, and then we have a couple of more lectures. And really, we have reserved time for the bigger component of this course, which is the project. Okay, and so really try to spend as much as possible time. I mean, if you're devoting whatever bandwidth to this course, a good chunk of that for the next month should be for the project, because that's a big multiple of assignments. So assignment 5 is released already. It's due 2 weeks from now. It's going to cover concepts from today and next lecture. Okay, so it's not, you cannot probably, I mean, if you already know the material, you can start it today. Yeah, so it's going to cover 2 things from this lecture, next lecture. And importantly, there is 2 sessions reserved for students to present. They are online at the moment. We'll see if we want to make it in person, but currently they are online. Okay, so that's the outline. Just wanted to briefly mention the assignment number 5, which so assignment number 5 is again, most as you saw in the theme of the course, we're not trying to capture complicated models. We're trying to get the simplest models and really understand all the all the details corresponding to our choices, assumptions, when the models work and not work. So the assignment number 5 is a mix of, is basically mostly about generative models, and then a little bit about an unsupervised learning technique, which we'll see next time. So the first question is about naive-Bayes text categorization. It uses the same data set as assignment 4. The same words, on word frequency examples that you had. Okay. So same as problem number 3. And question 2, I'll just mention the topics now because we haven't seen much of this yet. Today we'll see naive-Bayes models. The second one, which we will also cover, is called hidden Markov model. So which is again a generative model of data set. Okay, so it's a good, interesting foray into a model which kind of models something that you don't see. Okay, so we have mostly our models have been supervised learning models. So of course, all the feature vectors are observed. Sorry, all the feature attributes are observed, and then you try to make a prediction. Hidden Markov model is a model where you kind of hypothesize that there's a missing feature that you don't observe, and assuming that such a feature exists, kind of helps you model a time series problem. Okay. So that's what the hidden Markov model is. I will not, will not discuss the details today. And the last question, just the next 2 questions, 3 and 4, are mostly about unsupervised learning. So k-means clustering and principal common inverse. Okay. So these are 2 techniques for doing some analysis on data, which doesn't need supervisory signal, as in you don't need to explicitly designate one of your feature columns as a target or a class, class to be predicted. So they are simple problems. So in fact, this problem is very similar to the SVM problem that you saw in the previous assignment. And principal common analysis is kind of understand, hey, if I do dimensional reduction, how does it influence my clustering results, basically. So those are the topics at the topical level of this assignment. Again, it's given hopefully if you work hard on the first 4 assignments, should not take too much time, and it's designed in such a way, and in fact kept it at a level so that you can spend more time on your project. Okay. So with that, let me jump right back into where we left. So where we left is actually lecture 8 towards the end, last couple of slides. They're actually part of this slide deck as well. And so I'm going to start from this slide deck, which starts with a little bit of review of the difference between generative modeling and discriminative modeling again, which we did last time, and then we'll get into some examples of generative models, and so we'll see that. So this is not a fresh start. It's just basically a recap of what we did last time, and then we'll do a version of basically constrain the maximum likelihood. So basically, when you're doing maximum likelihood on a constraint space, okay. So that's going to be new, and then we'll see some simple generative models, maybe being one of them. Okay. Let me. This is not relevant. So, I mean, this is just trying to say that although we are getting into a lot of minute details of elementary models, relatively comparatively to think about what to use in your profession, we'll probably not be using just these models that we've been seeing in the course. There will be many other models that you'll come across. But this is trying to at least, maybe this Venn diagram is not accurate, but it kind of shows the different fields and topic areas that are relevant. If you're going to, be in this area for the next 20 years, 30 years, you may not be a master at everything, but you may need to interface with certain other topic areas, or you have to work with people who are experts in those topic areas, right? So some of you have software development or software engineering background, and so for you guys, this part will be easier. But intersecting with domain knowledge and math and statistics is going to be relatively new. Similarly, if you're heavily into computer science and then a little bit of math, then machine learning may be a good area to be in. Okay. But a lot of it actually for us in the base school, it really is heavily dependent on which business you're working for or working with, and what the goals are. Okay, that's a perspective that is kind of unique to non-engineering solutions or courses that you might have seen. It's really what are the business goals, and how to backtrack and come up with a potentially a statistical or other technical solutions there. Okay. So we are kind of touching in this cell here, machine learning and data science. In fact, as you'll see, as I said in the first lecture also, we are just trying to use a little bit of professional language while talking about some example models. That's what we're doing at the end of the day. But that language, hopefully that training will help you talk about other models later on. Okay. So I guess the question at this point is, why do we learn all these, these particular statistical models? Why not those others? And maybe they perform better in practice and so on. And whether what's the value add, right? Why am I spending like 3 hours every week in the lectures, and then maybe more hours offline? And the answer is basically you have to walk before you run. And so these are just elementary building blocks. So if you can really reason about them really well, via your coding assignments, putting assignments, or the discussion during the lecture, then hopefully that will make you a well-rounded data scientist or a business analyst. Okay. So this is just an illustration again. This is not exhaustive in any way, or it's not the only way to slice and dice different topics. But if you think of the ML bucket in that the previous Venn diagram, you think of techniques, right? So techniques broadly, and this is not the only classification, can be broadly split into unsupervised learning, supervised learning, and an area called reinforcement learning. We are not talking about reinforcement learning in this course, but if you think of unsupervised learning and supervised learning, we have spent a ton of time on supervised learning, right? We looked at classification and regression. So we're starting from KNN, decision trees, and most recently SVMs in the assignment. We've been looking at classification and regression, and here are some example problems that you think have maybe seem like textbook problems, but it's actually problems that companies face every day. Customer retention, for example, if you're an app on the App Store, then you see people signing up, people signing off. You're concerned about, hey, what should I do in my app so that I can retain more folks, right? So although it may seem like a textbook problem, it's actually a problem that their teams literally getting paid to work on every month, every day, right? So So here I've just highlighted classification regression circles, which is what we spent a lot of time on. What we're going to do, later on, not today's lecture, later on is, or next lecture is going to be dimensional reduction and clustering as a way to do exploratory analysis. Okay. So when you get data from third-party sources, or your own collecting data from your, from your own app, or data, from a data vendor, you have to kind of first understand what are the attributes there, how do they relate with each other, and you've done some of these elementary analysis, exploratory analysis in your assignment. But here, the ask is really a little bit more to further understand the patterns in the data. Okay? Don't worry about supervised signal, further understand patterns in the data. And two of the circles here, these are not the only unsupervised learning techniques, but they are just trying to, for example, dimensional reduction is saying, hey, out of these 100 covariates or features, which are the prominent ones. And clustering is saying, hey, is there a natural grouping of my data points, which kind of maybe will give me segments of customers. Maybe different customers have different, streams of behaviors, and maybe naturally, just without even a supervised signal, I can figure out that, hey, this is the set of customers who only go to my app in the mornings, and maybe only use my app in the afternoons, something like that, for example. Anyway, so that's the high level, pitch again. And let me come back to where we were last time, and what we're going to do today. So last time we did start, we kind of finished some parts of model assessment, and then last time we were talking about generative versus discriminative models. And we will briefly recap that. In fact, briefly recap supervised learning, the difference between generative and discriminative models. And today there'll be three major things that we'll try to do today. One is parameter estimation review. It's a review, but a new thing will be that we'll try to estimate parameters of a multinomial distribution. Okay, and so estimating the parameters of a multinomial distribution will have one extra new thing to know about compared to estimating parameters of a binomial. Okay, or estimating parameters of a Bernoulli, which is something that you did in assignment as well. Okay. So that's one thing. And the next thing we'll look at is Gaussian discriminant analysis. It's again a supervised learning technique, but it's a generative model, and we'll contrast it with logistic regression, for example. Okay. And the last one for today, at least, is going to be naive-Bayes model. Again, it's a supervised learning model. So today is really not about unsupervised learning. Next week, perhaps. But these are examples, simple examples of generative models, but simple enough for us to understand what is generative model bringing to the table compared to a discriminative model. There's a whole class of modeling techniques. Just as a teaser, there's a called graphical models. Okay, fancy name, graphical models. So it's basically out of which all these things that we're describing today can be thought of as examples. Okay, thought of as special cases of this graphical model framework. So if you're more interested, there's actually a 1,000-page book on this topic titled Graphical Models that you can look into, which I can suggest afterwards. Okay. So it's a very, not just these methods, Gaussian discriminant analysis, naive-Bayes, and so on, but graphical modeling techniques help you encode domain knowledge really nicely, really smoothly compared to in an ad hoc fashion. Okay. So when you are in a domain, let's say healthcare or automotive industry or financial industry, you may have a lot of domain knowledge, and which means that relationship between attributes, and maybe some attributes are not related, condition on some other attribute, and things like that. That information can be very nicely represented using a graph between these attributes, okay, with nodes as these attributes. And so it was prominent before, I guess, the deep learning decade of last decade. It's still prominent. I think it has still a value in using domain knowledge to quickly get some nice models running. Yeah. So anyway, let me come back to our review of supervised learning and why generative models may make sense. Okay. So in discriminative models, which is what we've been spending the first, I guess, first 6 lectures on, is we have been given a data set. Okay, so it's a problem of like reverse engineering the function that related x's and y's, right? So we have a data set which we, this assumption IID and drawn from some unknown distribution is only needed in theory to kind of justify some of the actions that you're taking. In practice, you have a data set, you can always call a function, like a fit and predict function, and get away with some performance. But here, this language is just for us to kind of say, hey, something is reasonable, something, the decisions that we're making in terms of what model to pick, or what is the setup, that's where I think these additional, I guess, assumptions make sense. So we assume IID data for now, not time series or anything, or dependent data. And for example, the graph data would be dependent, okay, where nodes are related to each other with some unknown joint distribution. So we are saying there is a joint distribution, but we don't care about it. Okay? In discriminative modeling, we don't care about the joint distribution, although we do care about the joint distribution as a part of this test error that we define. Right? The test error is defined according with respect to the joint distribution between x and y. Okay, but we don't care about estimating this quantity directly. We care about estimating the function which relates x and y, so x to y. So we've started a hypothesis space, which is this script hex notation here. This is a set of all linear functions, the set of all decision trees of certain depths and things like that. And you find a particular function in this set. Okay, that's what a model optimization set is, right? So you're basically finding, when you find parameters theta naught, theta 1, theta 2, you're just saying, hey, my set of models is any such vector. So it's basically the whole vector space, out of which I'm getting one of these vectors, right? So if you just focus on loss, then it's called empirical risk minimization, in this, I guess, terminology. And if you, for example, add a regularizer, it would be called structural risk minimization. Okay. And this is just, again, not super important for practice, but this is a terminology that kind of was developed in 2000s and a little bit before. And there is a typo here, but basically, either if you kind of want to build a discriminative model, you really focus on decision boundaries. So either you try to find a linear decision boundary, and that's via SVMs that you're currently working on or finished working on, or logical regression. Okay? So these two are examples of approaches where you will basically get a linear decision boundary. Okay? Or you try to actually find a nonlinear decision boundary, which is via decision trees or kernel SVMs. Kernel SVMs is something that we have not explored in the assignment or in the lectures, but kernelization is an interesting idea in itself. Okay? But essentially it gives us nonlinear decision boundary. Okay? So maybe potentially better fit for data. So not always, but many times, all these, some of these approaches, when they try to find decision boundary, that finding of decision boundary, so finding a function is equivalent to finding a decision boundary or whatever the representation of decision boundary is equivalent to finding this conditional probability. Okay? So not always, but sometimes. This conditional probability of y given x. Okay? So for example, for logic regression case, this logistic function that we're using, a sigmoid function, is basically, you can interpret that output to be the conditional probability of the class label being 1, let's say in binary class situation, given feature vector, right? But this interpretation is hard to kind of get. For example, when you're using an SVM, right? SVM is just going to give you margin from the decision boundary, so it's not exactly a probability. But some models give you that conditional probability. Okay. In contrast, in generative models, we are not only interested in the decision boundary. We are always interested in decision boundary. Generative models are discriminative models. Within the class of supervised learning, we always have to say, hey, what is the potentially new label for a new feature? But at training time, we are not only focused on getting this focusing on decision boundary. We also want to understand the distribution of features per class. Okay? Or in a study another way, we want to understand this joint probability between x and y as well. Okay? So, for example, this is just an example. Let's say you are doing a 2-class classification. You're classifying cats versus dogs. Cats are positive class, and dogs are negative. Then what we want to understand, and what not we want to, but like generative models will also try to understand, or at least model, is the conditional probability of the features of the dog class, okay, distribution of dog features. And we also get a handle on the distribution of CAD features. When I say get a handle, we understand just means that there's some parameters that determine these conditional probabilities. We'll estimate those parameters as well. Okay. And then of course, for example, how many dogs and cats we have in general. So why am I explicitly mentioning these? These all together, you can patch them up and you can get the joint distribution between X and Y. So if you have that, for example, let's say if you have these, let's say, instead of joint distribution, since I said we have these 1, 2, 3, 4 terms, given these four terms, you can easily see how to get a joint distribution. Here is an example where you're getting the marginal distribution of X, just the distribution of features. Okay. And distribution of features now, previously you were always thinking of, hey, distribution of features, maybe Gaussian, multivariate Gaussian or something like that. Here it's not the case. It's you can see you marginalize over the thing, over Y, which you don't want to have, right? Marginalize means average out, right? So remove Y by summing out over Y values. Y is less than 0 or 1. Then and then this joint distribution factorizes as the conditional probability times a marginal probability itself. So P of X given Y times P of Y. And you can see that, maybe P of X given Y is potentially normally distributed. P of X given Y is equal to 0 may be normally distributed, but P of X itself seems like an average of normal distribution. It also turns out to be normal distribution, but it need not always be the case. For example, one could be normally distributed, the other one could be maybe exponentially distributed, right? So now you're thinking of, hey, actually my distribution over my features, even one-dimensional, two-dimensional, need not look like a Gaussian blob, or need not look like a simple univariate or multivariate distribution that you are aware of. Okay, so anyway, given joint distribution, you can always compute a marginal like this. What we want to find, as I said, generative models, it's nice that they do something extra, which is understand the distribution of features under each class. But at the end of the day, we want predictions, right? So how do they make the prediction? They make the prediction just like before. So y hat is the argmax, okay, of P of Y given X. Okay, this is what you would do even for the even for the discriminative model. But the difference is, instead of focusing on P of Y given X, which you just compute by base rule. I said this is base rule, but this is just a factorization of joint probability into conditional probability, right, and the marginal probability. So you can factorize X comma Y in two different ways. So you just set them equal, and then probability of Y given X is just given by this expression, and that's exactly base rule. In this expression, you can see that when you do a maximization over Y, the denominator has nothing to do with Y. It's not a function of Y, so you can ignore it. Okay. So in fact, there's an equality here after removing the denominator, because we are focusing on the argument of the maximum. Okay. You can't just write max of this is the same as max of this, because there's a denominator missing. Okay. But you can always write argmax of one objective is the same as argmax of the other objective. For example, if the second objective is like 10 times the first one, for example, 10 is not useful. Okay. So that's how you predict. So what, why contrast these two? It's not really a contrast. It's really spending some time on, one could be better than the other, depending on your, depending on the application. Okay. So as toy problems in textbooks or in the lectures, you may not see a big deal of a difference between discriminative and generative models, but generative models encode more, can allow you to encode more information in your problem. Encode more domain knowledge into your problem. And so if the domain knowledge is actually correct, then you don't need too much data to actually estimate things in your problem. Okay. So let's talk about discriminative models. If directly just interested in finding a discriminating decision boundary. So they typically can get you a handle on conditional probabilities. Sometimes they don't, but you can always do some post processing to get some estimate of conditional probability that you can interpret as conditional probability. Classification performance is generally better, okay, on average, okay, better than, let's say, generative models. And that's why generative models are really it's not an apples to apples comparison, because generative models, you're really hedging on the fact that your domain knowledge is correct, and therefore you can do better than a more broader technique. Okay. The con of discriminative model is you're not really focusing on how the classes themselves look like. Like if you do want to do more EDA, argument with more EDA or understanding what each class means, things like that, doesn't yield anything directly. Of course, you can use the data again to do some EDA. That's always possible. Okay, in contrast, generative models are interested in learning the distribution of individual classes. Okay, per class, how does the distribution of my features look like? So they model basically the corresponding probability of x given y instead of y given x. And of course, they also model probability of y. So this is another way of saying they just model the joint probability of x and y. Okay, and make predictions via Bayes rule. Pro is we will learn something about each class because we have this object. Okay, and this object basically, when I say we have this object, we have the parameters of that object. Okay, and of course, the pro is it will perform better if it is actually the right domain knowledge. Okay, so if you already kind of know much about your problem, then you don't have to waste a lot of statistical power to identify relationship between x and y. If you already know something of relationships between x's themselves, like features themselves, as well as the relationship with respect to y, then you should encode it, and that's what a generative model helps you to do that. Of course, the con is if you choose something incorrectly, then you will be massively biased towards your domain knowledge, and so you'll be off. Okay, so you'll be worse than discriminative models. Okay, so just wanted to spend, that was a review actually. So we'll get back to parameter estimation. As I said, we have actually seen parameter estimation a couple of times with maximum likelihood estimation, even in your assignments before. But what's going to be new is we're going to do something with some constraints. Okay, and so a good example is, as I was saying, is multinomial or categorical distribution. Okay, so I'll mention what they are. So let's start with the simplest one that you've already solved in assignment, in one of the assignment questions, assignment 2, I guess. So let's say you have a coin flip, and so this is a Bernoulli situation. So each data point is basically either heads or tails, and you map it to 0 or 1. And you have one parameter for this Bernoulli distribution, which is the bias of the coin. Okay? So which is the probability of head, let's say. So P is the parameter that you want to estimate. And given this particular observation sequence, okay, you probably did 6 trials, 4 times head and 2 times tail. Then you have a function, likelihood function, which is p to the power 4 and 1 minus p to the power 2, right? So this is kind of clear. We had a similar example in the assignment. So parameter estimation is just, hey, what is the parameter that maximizes the likelihood of the data that I've observed? Data that I've observed is already given, fixed. We're not changing that. So which parameter tells me, kind of supports the data that I've observed? That's maximum likelihood estimation. It has its own pros and cons, but we'll not get into the details. But let's say we are maximizing likelihood here. And so the goal is to just maximize this, right? So now this is a one-dimensional function. So just a function of phi. Phi is a number between 0 to 1. It's bounded. Okay, it has to be between 0 and 1. It's the bias of the coin. So for example, so that's what's written here. So what is the argument that maximizes this f function, f of p? F of p is just this p to the power 4, 1 minus p squared. Okay. So now how do you do this? I mean, if you didn't if you didn't want to do it by gradient descent, if you want to do it numerically, then this is an example of taking derivative and setting it to go to 0. That itself is what is called a necessary condition. Okay, we will talk about necessary condition again later, but I want to mention here itself, taking a derivative set equal to 0 is going to give you solutions. Okay, setting it to equal to 0 means taking a derivative set equal to 0. It's an equation. Okay, with one unknown phi. You can solve that equation, and so you get some candidate phi, so one candidate phi. Whatever solutions you get, those are candidates for maximizing the original objective. They may be actually minimizing also. So you don't know whether they're maximizing or minimizing, but just evaluating the derivative is equal to 0. Okay, so you also have to check for the second derivative, which is not being shown here, but you need to typically check for the second derivative, or you check for, hey, what is happening before and after that function. So here, the second derivative, instead of second derivative check, we are saying, hey, what happens when you're slightly less than 2/3? When you're slightly more than 2/3, it looks like the function is greater than 0, and the function is function is greater than 0 and function is less than 0. Is that correct? The function value is greater than 0 and function value is less than 0. Okay, this is probably not the right thing. What I want to say, is that you need to do a second derivative check. Okay, and this is something, I mean, this is not new. You might have known this. So anyway, I don't know if this check is correct, but basically here is a candidate, and you have to check once more to see whether that is a maximizer. Okay, so that's what you need to do. Okay, so in one dimension, that's kind of very clear. You can draw the curve also, and you can visualize the curve event and do this. Here's a second option, and this is also something that you've done before, which is you can take a monotonic transformation of this function. Okay, so if you instead of maximizing FP, you can maximize the log of FP, and this is a common trick that we use for maximizing likelihood. Okay, instead of maximizing likelihood, we maximize the log likelihood. Okay, and so if you take a log, then you get a function like this. Okay, 4 log p, and then you maximize this function, and this function, seems a little bit simpler than the previous function. Log of p, the derivative is 1 by p, and similarly, log of 1 minus p is minus 1 by 1 minus p. And so given that, you also get a solution 2/3. Again, this is a solution by setting the derivative equal to 0. So you have to again check for curvature, okay, at that point, okay, whether you're maximizing or minimizing. And as I said, just setting the derivative equal to 0 is just a necessary condition, unless the sufficient condition is the second derivative is negative, right? So together, they both of them are needed to kind of certify that this is a theta that this is a phi that maximizes the function, right? So anyway, that was a recap. I wanted to use the word necessary condition because we'll see that in the next slide. Any questions here? Yeah.
So we can take any monotonic transformation, but why do we talk about log everywhere?
Log makes the exponent simpler, right? So brings the exponents into your front. Okay.
Even in the categorical, we did log just because of that.
Yeah, especially with many of the exponential family functions. If your distribution is in the exponential family, then it's very natural to take log of that and get away with not dealing with exponents and all sorts of calculus with exponents. Yeah.
But we can take any monotonic transformation, and if we take, does the result vary in terms of the?
It should not, right? I think we proved it in the class or somewhere else, maybe in the assignment. Yeah, that even if you use the monotonic function. So yeah, for example, log's domain is between 0 to infinity. Okay? It cannot take a negative value. Okay? And so log of if x1 is less than x2, then log of x1 will be less than log of x2. Okay? When x1 and x2 of course has to be positive. So you need to take such functions. Okay, log is a good candidate. Yeah. But log is not the only candidate. Okay. So now what we're going to do is so previous one was example was really Bernoulli parameter estimation. Okay. So now what we are trying to inch towards is a categorical distribution estimation. Categorical distribution is just is a generalization of Bernoulli. And so you'll see that you need a little bit more thinking here. Of course, there's a mechanical procedure to do this estimation as well. But let's try to understand like what changes. So here's a string, bunch of basically a text. It has words, basically six tokens and 56 words. Words are just these ones. Some of them are highlighted. We'll talk about the highlighting in a later slide. But it has few words, and tokens just mean like some extra things, okay, like a comma, whatever this quotes and so on. Okay, so don't worry about it. It's just a text blur. We want this to kind of build what is called a unigram language model, and it's a fancy name. At the end of the day, we're just creating a categorical distribution, okay, over words. That's what we want to do. Let me explain that here. So basically, each word x, you can think of each word x is a sample from some distribution. Okay. So how many words are there? I mean, 56 words. So think of a 56 word distribution. This 56 support probability mass function, and if I sample something from there, and I'll get some word. Okay. For example, Alice, or beginning, or reading, or something like that. Okay. Of course, it will not be in this order. Okay. This is particularly generated, but the model is of course not sufficient to generate a sequence like this. But the model is just trying to kind of understand the frequencies of these words. Okay. That's what the model is doing. So what are the parameters of this model? The parameters are just going to be the probability masses at different words. Okay. So the probability masses are, what's the probability of Alice? Maybe let's call it phi Alice. What's the probability of without? Let's call it a phi of without, and so on. So one parameter per word, basically. But of course, the 56 words, you only need 55 parameters, or you can keep all 56. Okay. So okay. So how do we estimate the parameters? So the unigram model is just this P of x itself is called the unigram model. So P of x is nothing but a probability mass function. We're just calling it a unigram model. It's a multinomial distribution, or yeah, you can call it a multinomial distribution or even a categorical distribution. For us, for now, it's not a big difference. Let's call it probability of the word xi to be pi. Okay, instead of using the subscript word itself, we're just indexing it by some number, and let's call it pi. Okay, parameter for that word. Then the probability of a collection of words, okay, or a sequence of words where the sequence information is kind of ignored. Probability of collection of words given the phi vector, okay, so the phi parameter set is given by this multinomial expression. Okay, this is just the PMF for a multinomial distribution. So what are the symbols here? N is just the number of words that you've seen. Okay, and C of xi, C of x1 and C of xn, these things are just counts. Okay, counts of these words. Okay, some words may be repeated a few times, so then you're just counting them. Okay, and so this is a product, and so every time a word appears, you're kind of multiplying a phi for that word, and so of course some words will have some extra count, so that's why there's to the power. Okay. Okay, so that's nice. So this is the distribution, and now we want to estimate the parameters of this distribution, which is just the phi. Okay, what is the data here? Data is just a count, p of xi. Okay. So basically you have a collection of these words, and what is the generative model assumption we're making, or not generative model, but a distribution assumption we're making is that data is indeed generated from a multinomial distribution. So you can see that, hey, we're making an assumption. If the data doesn't correspond to that distribution, then you are kind of in a bad situation. But here, this assumption is quite minimal. So given this assumption, what is the log likelihood? Log likelihood of this expression, you can kind of ignore. You can see that this whole term is just not related to the parameters, just a data, right? So it's fixed. It doesn't change with fees. Okay, so it's a constant. So if you take a log of this whole thing, it's some constant number. I don't know. Seems it's a positive number. So log of that is fine. So it's gone. Now this product of phi to the power c just becomes sum of these log phi. Okay, that's kind of clear, right? So this is the log likelihood, and we want to maximize this, but we have a constraint that sum of the phi should be equal to 1. Okay. So if you think of 56 parameters, then the sum of 56 parameters should be equal to 1. Or you could say, hey, I only have 55 parameters and not have this constraint, but there will be one log term which will be 1 minus all the other 55 terms. Okay, so either there will be complexity in the objective, or there will be a constraint. Okay, so let's stick with the constraint version, because that's the example, that's the discussion I want to have. Previously, we did have a constraint. Even in the Bernoulli, we had a constraint that probability of positive plus probability of negative is equal to 1. But then probability of negative, we just stored it as 1 minus probability of positive, and that's why the objective function was phi to the power 4, 1 minus phi to the power 2, or something like that. Okay. So we had the same constraint. It's just that we kind of got rid of the constraint by just plugging the probability of negative to be 1 minus probability of positive. Here, if you do that, it's going to be kind of a little bit more messy. It's 1 minus a huge bunch of terms. You can do that. You can do that and just ignore the constraint and ignore this particular constraint and do gradient descent, for example. But there is a further constraint. Okay, so in the Bernoulli case, the constraint was that the phi value should be between 0 and 1. So the domain was kind of has to be between 0 and 1, right? So it cannot be less than 0 and greater than 1, right? Here also, each of these p's has to be between 0 and 1. Right? So there is a bounding box constraint, basically. But we'll ignore that constraint for now, but that constraint is there. Okay. So let me briefly mention, a necessary condition for constraint optimization in general. Okay. So this is just an intuition building slide, so it's not really, maybe a denser slide for this session. But let's say you wanna, in general, maximize a function f subject to some constraint g. Okay, so this is how people use language, right, to kind of express what they're trying to achieve, right? So here they're saying, hey, I want to maximize some function subject to some function g. Of course, you in application you will specify what the f function is and what the g function is. So how do we do that? Okay, so so the way you want to think about this is basically, if you think of a maximizing over parameters, okay, we have just said x and y explicitly here. Sorry, maximizing over the decision variables x and y are typically the parameters of our distribution. So x and y, just think of them as two dimensions. So sorry, two coordinates. Okay? So don't think of x and y related to a supervised learning setting. It's just theta1, theta2, or something like that. Okay. So why explicitly theta1 and theta2? Why not just theta1? Just for simplicity. It just gives a flavor that it's a multi-dimensional optimization. Okay, so if you want to maximize this, basically there is some x star y star. Let's say it does achieve the maximum. Okay, that means that f, the value, the function value, cannot be increased when in the direction of any neighborhood point where g is equal to 0. So what do we mean? So let me repeat this simple this sentence here. What I want to say is that let's say x star and y star are achieve f maximum. Okay, achieve maximum. Then we're just looking at the definition. Oh, hey, they achieve maximum, but they are on this. They also satisfy this constraint g of x comma y equals 0. Okay, so if there is any other point on in that neighborhood which also satisfies g of x comma y equals 0, of course they will not be. The function value cannot be increased because that disagrees with the definition that they are the best, right? They are the maximum. Okay, so how do we think about this maximum, right? So you can walk around along the contour of g is equal to 0. So contour of g is equal to 0 means just think of g. So that's why we use two variables x and y. So think of a plane, okay, plane of decision variables. X is one x-axis, y is y-axis. So the constraint g of x comma y is equal to 0 is something like some curve in this plane. Okay. So what we're really doing is we're walking along this curve, okay, or we are navigating along this curve in the 2D plane for this illustration until we reach some points where f should not change. Okay. So f should not change. So if f is fixed, maybe so think of f is a function of two variables, right? So if you can think of it like a peak and valleys and so on. So on the contour as you're walking, there may be some part where f is not changing. Okay. So they are candidates for local optimum, okay? Because if f is changing, it's going from high to high again. Maybe that part where f is not changing, or even one point, could be local minima, for example. Okay. So there was a question about IID. IID means independent and identically distributed. Okay. Let me come back here. So now what we want to establish from this slide, this illustration, is get a sense of what is a necessary condition for some point x star y star to be an optimum. Okay. So it's very similar to the one-dimensional setting. As I said, setting the derivative equal to 0 is just necessary condition. Okay. But it's not sufficient in the sense that you have to check the second derivative also is like is negative, for example. So here, what I want to motivate towards is that, hey, what is the necessary condition for this setting? And for that, we're going to define the necessary condition using a auxiliary function. Okay? The auxiliary function is called a Lagrangian. The Lagrangian function is just made up of, hey, whatever is the original problem, take the objective, take the constraint, or the left-hand side of the constraint. Let's say the constraint is like this. Okay, maybe the constraint has the right-hand side, which is 10 over here. Okay? Then you just make g of x, the new g of x comma y as the old one minus 10, so that it exactly looks like this. Then here is the candidate auxiliary function called Lagrangian, and we're gonna specify our necessary condition via the Lagrangian, okay, via this auxiliary function. Okay. So let's think about this point here a little bit more. So when can this happen that you are walking along the contour of g is equal to 0? So g is equal to 0, some curve, and when can it happen that you have a okay, let me rephrase this. So you're walking along the contour g is equal to 0, and you reach some point where f is not changing. Okay. So they are good enough to be local optima. So the first case, so this setting we can describe in two ways. One is the contour of f of x comma y is equal to d, okay, for some d, and the contour of g of x comma y, which is some curve. So there's a curve on x comma y plane for g, which is fixed, and we are saying, hey, the f is some your function, but f we can figure out a contour just like hill plots that you see in maps, right? So let's say the f function, you set it equal to d, okay, that will also give you another contour. So in that region, those two contours could be parallel. Okay? Those two contours will be parallel to each other. So what does it mean in terms of Lagrangian? Is that if you take the gradient of the Lagrangian and set it equal to 0, okay, at these local optima, so gradient of the Lagrangian set equal to 0 at the local optima, then the case 1 corresponds to that the gradient of f is, if you can just look at this function, right? If you set the gradient of Lagrangian with respect to x comma y equal to 0, then you can see that this minus lambda, so the gradient of f minus lambda gradient of g equal to 0. So which means that gradient of f is equal to lambda times gradient of g, right? Right? This is just by definition. If this is true, if the Lagrangian is 0, then this is true, right? So this expression here is exactly capturing our case 1. So if think of the gradient, gradient, remember, is a kind of a vector in the input space. So in the xy plane, there is some vector, and we're just saying that the vector for the gradient of f, which is some vector, is in the same direction, is like a multiple, like a scalar multiple of the gradient of the g function also. Okay, so they're like basically two vectors going in the xy plane. Just think of like two vectors in the same direction. That's what this if the Lagrangian is equal to 0, this is one outcome. The second one is that the gradient of f, okay, so the gradient of f is equal to 0, and so gradient of f is equal to 0 on x comma y, which means that it has potentially, let's say, think of maxima, it has stabilized when we are doing this walk. So remember, this whole condition is we're walking around g is equal to 0 contour, and somewhere f is not changing basically, and that f is not changing because gradient of f is 0. Okay, that is the second case. Okay, so in this case, so how does case 2 correspond to our our necessary condition of building via the Lagrangian? So if Lagrangian is 0, then either this is true, or further, if the gradient of f itself is 0, then by definition we know that by definition this is there. So if f is 0, then it doesn't matter what the gradient of g is, lambda should be 0. Okay, so what we're trying to say is we are trying to capture when can we have a local optima on given we're walking around the constraint, or so walking on the constrained region. And for illustration purposes, we are thinking of constraint as a curve. It's not always a curve. In higher dimensions, it can be a subset at a particular space. Okay, but for simplicity, let's keep it a curve for now. So basically, the objective of this slide is just to say that if you have an original objective function, and if you can define a Lagrangian, then a necessary condition for a solution x star by star. Okay, Lagrangian also has one more parameter, so let's there's lambda star as well. But a necessary condition for x star by star is that this Lagrangian, the gradient of the Lagrangian has to be 0. Okay, that's all. So that is kind of how does it differ from the previous situation? We already knew that we wanted the gradient of f, or basically the derivative of f, is equal to 0, right? That was a necessary condition in a previous case, right? So it's very similar to that. Here we are saying that the gradient of Lagrangian has to be equal to 0. Okay, that's a necessary condition. Okay. And there are a few more conditions that are needed to kind of also say they are the maximizers. But for now, we're just going to do very similar to what we did in the one-dimensional case. We're just going to say, hey, what is the necessary condition? And there's extra checks that are needed to say that is actually the maximum. Okay. Here is just the Lagrangian gradient of the Lagrangian has to be 0. So let me actually show via the picture, which I should have done once, this slide first and the next slide before afterwards. So let me recap. So if our goal is this, and in 2 dimensions, it's a little bit deceptive, at the same time a little bit informative. So y decision variable are here and x decision variable is here. You want to optimize f while optimize x comma y by maximizing x comma y that maximizes f. Subject to that, this that x comma y lies on this curve. Okay, let's say this is the curve where g of x comma y is equal to 0 percent. So you can only pick. So you cannot pick x comma y arbitrarily. The x comma y has to be on this red curve, right? So the first version was just saying that, hey, if that is the case, then if I think of contours of f of x comma y, my other function, right? There'll be some contour which will, let's say f actually, if the red curve was not there, and if I wanted to maximize f, then it will be x comma y somewhere over here, which will be the maximum. Like if you look at the top view where my cursor is, that will be the maximum. But since I'm constrained, I need to have a contour which just touches the red curve, and there the 2 gradients have the same direction. Okay, so in the sense that the gradient of f is the same direction as gradient of g. Okay. Over here, and you can see the gradient, I guess, arrows here, but these are multiples of each other, scalar multiple of each other. One can be going, I mean, the scalar quantity can be positive or negative, so that's why you see a red curve this way and I guess a green, the dash curve the other way, but basically they are parallel to each other. That was case 1, right? Case 2 is not shown here, but basically in case 2, you just so you are achieving so your constraint g of x comma y equals 0 is not exactly, may not be exactly like this curve. Maybe it's the full region, and there wherever you have hit a first derivative is equal to 0, or basically the gradient is equal to 0, is enough to is enough. So any questions about this? Yeah.
Any way generalization of the simplex on algorithm that is not linear programming?
It's not related to simplex. It is related to simplex in some way. It's an intuition for what is Lagrangian. So for other, simplex is an algorithm for solving a linear program. Okay, it's a but here the simplex is an algorithm, so it has a sequence of steps. It's a procedure, right? The procedure is not exactly constructing the Lagrangian as such. So the Lagrangian is a concept related to optimization. Clearly, it's related to constraint optimization. And simplex is a algorithmic procedure. So there's a difference between a concept and a procedure. But the procedure solves constraint optimization. Constraint optimization in particular, when f is linear and g are linear, I guess, inequalities, then simplex is an approach to get to x star y star, right? So just trying to kind of, they're not unrelated, but at the same time, they're kind of addressing different aspects.
It's not that simplex at a higher dimension, this is how.
No, simplex is when you kind of, if f is linear function, like x plus y, and then g is a linear function, like 3x plus 2y is equal to 0. Then you can apply a simplex procedure to get to the optimal xy. Okay, get to the best solution. But that's a procedure. So here we are just talking about what is how to characterize, like what, like, this is the objective. There will be some x star y star that, let's say, that does maximize this. Like how to characterize that solution. Okay. So we haven't gotten the solution itself, because the solution itself is described in terms of, hey, that x star y star which satisfies this auxiliary function could be a candidate for the maximum. Whereas simplex is actually an algorithmic procedure, as in like a sequence of steps which will actually get you the maximum. Any other questions? I would say simplex, let's not talk about it here at this point. Yeah, but it's a good point. Yeah. So what I want to do, and the reason why I showed you this dense slide, is I just want to relate it back to what we know already, at least in terms of mechanical procedure, while doing parameter estimation. So let's come back to that univariate model. Okay, so we're going to do maximum likelihood estimation under this new constraint. The constraint, we already had constraints. We always have constraints. For example, in the Bernoulli case, I said constraint was that the parameter is between 0 to 1, right? So that's a constraint, right? Here we have an equality constraint, right? The sum of the fees should be equal to 1, okay? Which is the definition of a probability mass function, right? So the Lagrangian. So what we're going to do is, while the Lagrangian, get some candidate X star, Y star is possible. Okay. In fact, you'll see that in this case, it works out nicely that we actually get only one candidate X star, Y star, or in this particular case, only one candidate fees, and they happen to be the maximizer. Okay. So why are the maximizer? We are not showing it here. That's we are only focusing on the necessary condition. So the Lagrangian, remember, this was the log likelihood. If you remove, we drop the constant because constant is irrelevant. So sum over all the n words of count of those words times the log of the parameter related to that word. And this extra thing that we added minus lambda is this Lagrange coefficient. Okay. And this lambda times this constraint was just that this was the g function basically. Sum of Pj minus 1 is equal to 0, or sum of Pj is equal to 1. Okay, so the same thing. So this is the constraint. So to write Lagrangian this way is just a way to kind of understand, like we're fitting it back to our intuition from previous slide. Then what we do, so we want to generate a candidate optima, right? Candidate x comma y, in this case P1 to Pn. Okay. So how do we do that? We say, hey, to get a candidate, there is a necessary condition they need to satisfy, which is the gradient of f, gradient of the Lagrangian should be equal to 0. Okay. So what is the gradient with respect to? With respect to every Pj. Previous slide was just x and y, but here we have n variables, right? So with respect to each of the n variables, we have to take a derivative, and that's the gradient vector, and set the vector equal to 0. Okay, so we are actually getting a system of equations. Okay, so what are the system of equations? So first, like with respect to each coordinate, let's say gradient with respect to Pj is something like this of this Lagrangian. Okay, so you can see just the c remains, and log of p is 1 by p, and only some the p term remains, and so minus lambda is the only term remaining. Okay, so the gradient of the partial derivative of Lagrangian with respect to one of these parameters is just this, right? Do you guys agree? Of one of the coordinates is just this. When you have this huge function of Pj, if you take the derivative with respect to one of the Pj's, then only these terms remain, and then you can set it equal to 0, right? If you set it equal to 0, you can just relate, hey, how is this? So what part is the data? The data part is counts of xj's. Okay, those are the words what we observe. Pj is something that's unknown. Lambda is also unknown. Okay, so we have n such equations. Okay. It turns out for this problem, we just get a bunch of equations like this, simple equations. And then remember, we also had to take the gradient of lambda with the gradient of the partial derivative of the Lagrangian with respect to the lambda parameter, because Lagrangian is a function of lambda as well. Take the gradient, or if you take the partial derivative, sorry, you get the original inequality, the constraint back. Okay, the constraint is just saying sum of Pj minus 1 is equal to 0. Okay, so this second gradient was kind of not very useful, but basically that's just mechanical application of, hey, let's find the gradient of L with respect to all its parameters and set it equal to 0. That's a necessary condition. So we did that. Okay. So from the sum of Pj is equal to 1, what we can do is we can substitute the definition of Pj here, and so we get an expression for lambda. Okay. So this is the expression for lambda, and which means that you can plug the lambda expression back, and now you have an value of Pj which only depends on data. C of xj and basically C of xj, right? So what we did via this Lagrangian representation is figure out the solution to this constraint optimization problem. This is not the only way. This is not the general way to do constraint optimization. In fact, you cannot do constraint optimization via pen and paper, for in general cases. But it gives you a sense of how do you do MLE for beyond Bernoulli. Okay. So this is how you'd get. So you're basically just the ratio of terms, frequencies of different words. Okay, that was kind of obvious, right? So if you did not know all this stuff, if you just wanted some model of how frequent each word is, which is what the original unigram language model is, then you just say, hey, the first word appears 10 times, the second word appears 5 times. If my vocabulary is only 2 words, then it's 10 by 15 and 5 by 15. Right? So that's a TMF that you can construct, and that's exactly what we're doing here. Why that is the right construction is what we're justifying via this constraint optimization idea. Any questions? Okay, so so if you do that for this particular text blurb, you get some numbers like this. So probability of off is 3 by 66, and probability of her is 2 by 66, and so on. Okay. And so you can also have probabilities for these extra tokens which are not exactly words. Okay. That's good. So let's now extend the model. So we had that univariate model, the unigram model. Unigram, by the way, just means unigram means uniword, and n-gram means n words, and so on. Okay. So we're going to create a different distribution. Okay, so the distribution is the same text blur, but we're going to try to model the probability of two words together. Two words. Okay. So for that, we need remember, probability of two words is probability of, we already have from previous work probability of one word. Probability of a word is just, we computed using categorical distribution assumption before. So how do we get probability of two words? To get the probability of two words, we just need one extra ingredient, which is the conditional probability of the second word given first word, right? Because if I know the conditional probability and I have the marginal distribution, I can mass, kind of use them together, and I can get a joint distribution. It's the probability of two words, right? So for that, actually, it's easy to compute the conditional probability of the next word given previous word, which is just the probability of, second word given the previous word. What is the probability of off given tired is one. Probability of what is the probability of off given use is one. There's going to be many such pairs, right? So in fact, there's 56 or 66 different choices. So there's going to be many such pairs, but some pairs will have appropriate counts and some pairs will not have. So for example, what is the probability that if the word the appears, what is the probability that the next word is bank, right? So the is appearing 3 times. So the bank, the book, and the use, and sort of which only once is bank seen. So probability of the next word being bank given the previous word being the is 1/3, right? So it's just counting and normalizing. So given that, you can you can kind of see that this model with 2 words and model with 1 word, they're actually consistent. Okay, consistent. It's just a I guess an illustration of the law of probability. So what's the probability of the word off? Okay, the probability of the word off will be if off is preceding all these words. Okay, whatever words, I mean all the words in the vocabulary. If I then average out the preceding, the succeeding word. The preceding word here. If I average out the preceding word, then I just get the probability of off, right? That's the definition of joint distribution. If you marginalize out one of the variables, then you're going to get what remains is the probability of the remaining variables, right? So probability of off given tired and probability of tired, plus probability of off given use, and so on. Okay, so these are the only 3 expressions which remain for this text. Okay, so off is preceded by tired, off is preceded by and somewhere else off is preceded by use. Okay, that's it, right? So by the colors are just for words that are appearing multiple times. Okay, just so it's clear, it's not confusing. Yeah. So if you just plug in the numbers that we saw earlier, probability of off given tired, we know what it was. We had computed these conditional probabilities, and these marginal probabilities we had computed using our maximum likelihood estimation, which is just count divided by count, right? So you get 3/66, and if you do the same with the joint, like probability of off preceding another word, okay, which is probability of sitting given off. In this text, there's only 3 words which succeed off. Okay, of sitting, of having, and then of a. Then if you kind of average out, then you'll also get the same number. Okay. So just trying to show, hey, marginals and so conditional probability, marginal probability, and joint probability are all related like this, right? Any questions about this part? It's not really illustrating anything complicated. We built the conceptual part for this section was just about some discussion about constraint optimization. That's all. Okay, so with that, let's actually talk about Gaussian discriminant analysis. This is a generative model, and we'll talk about how it's related to an example discriminant model, which is in particular logistic regression. So let's start with that. So as I said, we kind of did a review of parameter estimation. Let's come back to our original narrative, which is about this discriminative models versus generative models. And remember that generative models, we are not only caring about the decision boundary, but also the distribution. Okay? In particular, distribution of the features given each class. Okay? For example, the classification setting. So let me briefly mention, we haven't seen PCA here in this class. We'll see PCA later. Okay, it's part of your assignment number 5. But I wanted to briefly mention at least from a motivation perspective, the Gaussian discriminant analysis that we're going to look at today, look at now, how it relates to PCA. Okay, so PCA, what does it do? And we'll talk about the like the details of PCA and really understand it more clearly next time. But PCA is basically trying to find a new basis. Okay, so it's like, hey, the original basis is x1, x2. Can I turn around, change the basis such that I can get access which maximize the variance in my data. Okay, so I can get maybe like this this new basis direction lambda2, for example, has high captures high amount of variance in this data. Okay, that's what PCA does. To find maximally varying access to reduce potentially reduce dimension. So for example, if I want to reduce dimension, I can say, hey, let me drop lambda1, and let's say lambda2 is the one-dimensional representation of my data set. Okay, that's unsupervised learning topic, which we'll talk about next lecture. But LDA LDA is just a special case of GDA, and Gaussian discriminant analysis. So what does Gaussian discriminant analysis do? Its motivation is to maximize some access that separates two classes. Okay, let's think of this binary classification. So we have two blobs of data. One is class 1, one is class 2. And what LDA is essentially trying to do is pick parameters such that you can separate the two classes. Okay, so separate the two classes and basically get the access. So here there's no rotational access, but basically, for example, if you like think of this blue blob and the green blob, if you project it down into one dimension, for example, project it down in this direction, they're both overlap. Project it down into the x direction, then they are separated. Right? So class separation and discrimination is what is needed. So basically, we're trying to fit two Gaussian distributions such that they are as separate with respect to each other. Okay, that's what we're trying to do. In PCA, we're essentially trying to just find basically fitting up a Gaussian distribution or covariance of the data. We're just trying to find the directions with the highest variance. Okay. So just some discussion. So really, we're going to focus on this. So let's think about before even introducing what is the what are the ingredients in an LDA or a Gaussian discriminant analysis, when to use it, right? So a discriminant analysis or Gaussian discriminant analysis is useful when you want to build a classifier, generally two classes, and you have features which are continuous. Okay, so which are continuous features, and there is no specific knowledge about the distribution of the individual classes. Okay? So you don't have knowledge of the distribution of individual classes, but you know that the distributions are comparable, like two Gaussians or something like that. Okay. And why discriminant analysis is exactly why we want to do generative modeling, which is we also want to learn the distribution of each example, which is the marginal probability over the inputs themselves. Okay, maybe this is of interest to you for that maybe it has to conform to some domain knowledge that you have. Okay? So for example, if you're just doing supervised learning, you're not even paying attention to how P of X looks like at all for any addition tree or any SVM stuff that you're doing. But here, you will have a handle on this, and you want to learn the probability of features for each class. Okay? So of course, for today, it's mostly just about understanding generative models. As I said, the bigger class of generative models include, kind of, you can look up generative models. Sorry, not generative models, but Gaussian graphical models. You can look up the literature on graphical models to get much richer generative models. Get an understanding of them. So let's actually just talk about now the how the model is set up. Gaussian discriminant analysis, basically, it will have a generative story. So generative models, by its name, will need to have a way to generate data. Okay, so once you specify the model, there's a generative story attached to it, which is that, hey, if you tell me the model, I can generate the data, which means I can generate both X and Y. Okay. So we have in the we'll be basically trying to relate to two class settings. So we have two labels, okay, which means we can generate a label according to Bernoulli distribution with the parameter p. Okay, we'll first generate a label, and then we will, depending on the label outcome, we'll either sample from a normal distribution with a certain mean mu naught with some covariance, or we'll sample from a different normal distribution with a different mean mu1 and a covariance. Okay, so if y happens to be 0, I'll sample x from this distribution, and if y happens to be 1, I'll sample x from the second distribution. So that's the generative story. First you sample y, and then given the y value, you basically is generating x based on two different distributions, okay, two different Gaussian distributions. So this is script n is just a Gaussian distribution. In fact, it's a multivariate Gaussian distribution. That's why we are using the symbol sigma, the Greek symbol sigma, right? So in particular, for example, let's say there are normal distributions in n dimensions, little n dimensions. So one thing you can notice is that we are having the same covariance here for both the feature distributions under each class. You can change it, but we'll talk about it in a second. So what is so this is the complete setup. So what we have described is a way to generate x comma y. Now we have generated x comma y. That means we have pretty much specified the joint distribution between x and y. If you have specified already the joint distribution between x and y, then you should be able to make a prediction, right? But since you have specified the joint distribution, let's look at the parameters and let's try to estimate them using data. Okay. The parameters are clearly, as you can see, there's a p, there's a mu naught, mu1, and sigma. So those are the parameters of this model specification, and we can estimate them. We can estimate them using maximum likelihood. Okay, so I'll not discuss that at this point. And we can predict one if the following condition holds. Okay, the following condition is just saying. So this, by the way, this probability of x given y is equal to 1 times probability of y is equal to 1 is nothing but probability of x comma y is equal to 1, right? So and you can actually further process that as probability of y is equal to 1 given x times probability of x, right? I mean, you can. So what I'm trying to say is that to predict 1 if this condition holds is exactly the same as before, which is argmax the probability of y given x. Okay. So that argmax is like pick one of the y will 1 or 0 depending on whether the probability of y given x is higher. Okay, so that's exactly the same condition here. And so let's briefly comment on like how do we estimate these parameters. So for Bernoulli, we can estimate just focusing on the y data, okay, the data which corresponds to the y variable. So you'll have we know that the conditional probability, sorry, the marginal probability of y is just p to the power y, 1 minus p to the power 1 minus y, right? This is the trick that we use even in assignment 2 and before. And similarly, the Gaussian distribution specification is something like this. So it looks like a very messy expression, but the important components are x, the mu naught, sigma, and mu1, and sigma also appearing here. Okay. So these are the full specification of the distribution, the marginal distribution over y, and the class, and the feature distribution under each class. Then the joint likelihood, becomes a likelihood over all these parameters, and likelihood as a function of these parameters is the we are actually specifying log likelihood, log of the product over m examples of the probability of seeing each pair like xi, yi, which is exactly our data set as before, with respect to these parameters, okay, p, mu naught, mu1, and sigma. Now this, as you know, this joint probability we just described as it can be split into probability of the class given, probability of the feature given the class, then times probability of feature. Okay, so these two parts is exactly specified here, right? So p of y given t is exactly this, and p of x given y, depending on whether y is 1 or 0, is exactly given by these messy Gaussian distribution expressions. Okay, and we can just maximize the log likelihood of the joint distribution. Okay. So I think the last point is just trying to make a distinction that in generative models we're trying to maximize the probability of the joint distribution and not the probability of the conditional not the conditional probability of data. Okay. So if you remember from Gaussian regression, from the linear regression case, where we did not have a distribution over x, but we had a distribution over y. So the conditional probability of y given x and parameters was normally distributed, and then we were just trying to maximize the conditional likelihood there. Okay, so because conditional on x, conditional on x, whereas here it's not conditional on x. It's a x and y are together. We are trying to maximize the joint log likelihood or joint likelihood. Yeah. X is a vector. Yeah, that's why you have a very messy Gaussian distribution expression here. Yeah. So X is an n-dimensional vector here. Yeah, it's a multivariate Gaussian distribution. Yeah, so X is a 10-dimensional vector, for example. Yeah. So this doesn't apply when, for example, you have categorical features. Yeah, for example. But the reason why we're even looking at this is to kind of really understand. I mean, you could have categorical features, then Gaussian discriminant analysis may not be applicable, but you will have some other model that you can define. Okay? And so if you define a different model, you'll still be stuck with, at some point you'll be describing the joint distribution, and therefore you'll have to work with maximizing that likelihood of the joint distribution given the parameters. Okay? But yeah, here X is a vector, but it just happens to be a Gaussian vector. Yeah. So as we saw before, the maximum likelihood estimation of parameters is quite easy, especially for Bernoulli case or the two-class case. You just, in fact, we saw this a few slides ago. The estimate for phi would be just the count of the number of times you saw class 1 divided by the total number of observations. Okay, so m is the total number of observations, and you're just saying, hey, how many times did was equal to 1? Okay, so that's simple. And then that's the bias of your Bernoulli, and the estimation of your mu naught and mu1. Okay, so I'm just writing the formula here, but if you actually take the log likelihood and take the derivative and set them to equal to 0. For the Gaussian case, the likelihood is such that there is no constraint. Okay, so the mean vector, okay, the mean vector and the so at least the mean vectors don't have any constraints. Okay, they can be each coordinate they can take any value. So it turns out the mean vector is just, hey, so the mean for the 0th class is a very intuitive idea. Mean vector for the 0th class is take all the data points corresponding to the 0th class and take their average. Okay, that's what this very messy looking expression is just saying, hey, maybe there are 10 examples in the 0th class, then or class 0, then take the average of the 10 vectors. That's why it's 1 by 10 times the sum over all the 10 vectors. Similarly, the remaining vectors will be averaged over here. So it's intuitive estimates, but they pop out of a maximum likelihood estimation problem. Okay. You can just use these heuristics, but then there's something that backs these heuristics. Like if you naturally pick some heuristic like this, maybe you can say that, hey, it's actually the maximum likelihood estimate of my specific objective assumption that I'm making. Now sigma is a little bit more involved, but it's basically again some sort of a you can estimate it from data like this. Okay, so we will not discuss the estimation of sigma, because sigma itself, by the way, the sigma matrix, it's an n cross n matrix. It's also basically an average of a bunch of outer products. Okay, so outer products are like if you have a vector, if you take an inner product, you kind of reduce it to a single number. Outer product is just the opposite. If you have a vector, you can take the column vectors and multiply with a row vector, then you get an n cross n matrix. It will be of rank 1. So whereas if you take a row vector and multiply with a column vector, and that's it itself, then you get one number. So basically is a summation of bunch of rank 1 matrices. And so this, by the way, it's not immediately obvious like why you get this, but if you take the likelihood objective, maximize it, then you'll get these expressions, which are all intuitive. So like sigma is basically the empirical covariance with respect to the empirical mean. So first you estimate mu naught, mu1, and then the mu's you kind of use it to define sigma. Okay. Yeah.
Isn't there any individual conditions on each variable that they need to be somehow have got similar distribution to Gaussian? Then only this GDA will go.
each coordinate, each feature you're saying, yeah, so we are saying that the full X vector is a Gaussian, multivariate Gaussian, right? So each component is also going to be Gaussian. So, so if you have a Gaussian vector, if you're Gaussian vector, then each coordinate is also Gaussian distribution. Is also Gaussian distributed. That's a property.
That is a prior condition or
Yeah, we are assuming that things are Gaussian here. So already we are assuming numeric, and in addition to that, we are assuming things are Gaussian. Yeah. For class, we are assuming the whole vector is Gaussian. Can be well represented by Gaussian. That's where I said, like, if you change the distribution, then this analysis will not work, but you will hit the same pattern of defining the generative story and then defining your likelihood function and then maximizing it. Yeah. Even if things are not Gaussian. But here we are only restricting Gaussian, so we are making an assumption that the feature vector is Gaussian. So each coordinate should be Gaussian as well. Okay, so what we discussed in the previous slide is actually called linear discriminant analysis, more popular name. That's because we are choosing the same covariance matrix. Okay, so both the classes under each class, the distribution of X is actually determined by the same covariance matrix sigma. Okay, and so if that is the case, then it turns out that the decision boundary. So we can get a decision boundary. Remember, we have completely modeled the joint distribution. So certainly we can model the conditional probability of Y given X. And if you look at conditional probability of Y given X and take the argmax, there'll be a point, there'll be a bunch of points where you don't know whether this probability of Y equal to 1 is greater than the probability of Y is equal to 0 or the otherwise. Basically, the two probabilities are the same. And so that line, if you draw it, which is the definition of decision boundary for two class problems, then it's basically going to be so to draw the curve, that's going to be a line. So that's kind of easy to see when you think of like two, like this is the Gaussian fit to the original data of X's and zeros, circles. And you can see that, they will intersect in a very symmetric way. So you have to kind of, you will get a line, okay, which kind of disambiguates these two blobs. And if you choose a different covariance, if you choose to use different covariances, then you will have a nonlinear decision boundary. Okay? So for example, on the left side is a linear decision boundary. I think this is by scikit-learn. And so if you use different covariances, it's called quadratic discriminant analysis, and it's a curve like this. So LDA, by the way, the reason so LDA also corresponds to a completely different model called latent ratio allocation in topic modeling, but you kind of want to specify what exactly is the model, especially if you're using acronyms. SVMs, I think, don't have confusion, but sometimes the models have confusion on like what we're talking about. So linear discriminant analysis and quadratic discriminant analysis are examples of Gaussian discriminant analysis. So we are making the Gaussian assumption. Okay, it's just that the covariance, whether it's same or not, just determines one or the other. Yeah. So let me just wrap up this part by talking about its relationship to logistic regression. Okay, that's so why logistic regression? Why not some other model? Because you'll see that both lead to the same conditional probability of Y given X. Okay, so in Gaussian discriminant analysis case, X given Y is normally distributed. So let's say we're talking about linear discriminant analysis. So X given Y is normally distributed with some mean, and X given Y is equal to 1 is also normally distributed with some other mean. Okay, then the conditional probability of Y is equal to 1 given X. Okay, given all these parameters, of course. This conditional probability can be, it turns out to be equal to 1 by 1 plus e to the power minus theta transpose X. Okay, so where theta is some messy function of phi, mu naught, mu 1, and sigma. Okay, by the end of the day, it's some bunch of coefficients which multiply X. Okay, so so this is something, it's a nice exercise to work through if you have time. So this is a nice expression, but we know that for the logistic regression case, we directly are assuming something like this. Okay, if you remember logistic regression as the hypothesis function specification was actually, hey, if you have to have a linear transformation of X with theta transpose X, we'll apply a linked function G, which was 1 by 1 plus e to the power minus Z. And so the conditional probability of Y given X was exactly modeled this way. Okay. So what the first bullet point is saying, if you do linear discriminant analysis, your probability of a class given feature looks like this, which is the same as logistic regression. But the converse is not true. Converse in the sense that if you assume the logistic function as the logistic function as a relationship between the probability of y is equal to 1 given x, that doesn't necessarily mean that the distribution of features given class is Gaussian. Right? So one way, Gaussian assumption leads to this expression, but just assuming this expression doesn't mean that you're making a Gaussian assumption on the probability of features given class. Okay. So p of y given x is a logistic function doesn't imply that x given y is a multivariate Gaussian. It could be others. Okay. We're not saying anything about, and that's because we're not saying anything about the distribution of x at all. Okay. When we just say something about the conditional probability of y given x. Whereas in GDA's case, we are saying everything about the general distribution. So of course, some derivative or some direction of it to the conditional probability of y given x, happens to be logistic like function here, but that's the opposite is not true. So GDA is not the same as logistic regression. I guess that's one I guess summary here. So question is, what makes a stronger assumption about the data? So it's clear that GDA is making a lot more assumption of the data because it's saying that the probabilities of features given each class is Gaussian, right? So it's making more stronger assumptions that you can see via this 2 bullet points, which are trying to say that even if you don't say Gaussian distribution, as long as x given y belongs to an exponential family, okay? Probability of x given y is equal to 0 belongs to an exponential family with some parameter, and probability of x given y is equal to 1 belongs to some other exponential family distribution with some slightly different parameter. Even just this, okay, so this is not Gaussian. Gaussian is also a part of exponential family, but any exponential family, then the conditional probability of y given x is linear. Okay, so conditional probability of y given x is a function like this, a logistic function. Okay, so this is exponential. So Gaussian is a special case of an exponential family function. Okay. So I hope that is clear. Okay. Yeah. So so as we saw in the previous slide, GDA makes more assumptions. So what are the pros and cons? The pros, it's a double-edged sword. Okay? I mean, if you make more assumptions, it can work out for you. So you generate some alpha basically. you gain some advantages, or you can lose something. So if p of x given y is indeed Gaussian, then GDA is technically it's called asymptotically efficient. Technically, it just means that if you have a lot of data, you are getting to the true underlying parameters. Okay, but yeah. So in other words, at least in theory, what we're trying to say is that if it is indeed true that things are Gaussian, then you cannot perform better than GDA, because GDA already assumes something which is already true in the data. So any approach which doesn't assume that has to first learn those patterns and then do classification, right? So what is the impact of that? If the assumption is true, you generally require less data to learn, or less data to get to a decent classifier compared to other approaches. Okay, in particular, logistic regression approach. That you can try. So synthetically generate some data according to GDA specification, and then see how much examples you need to get to some quality of classifier, and see whether you can you need the same or you need a little bit more if you just do logistic regression. You'll see that you generally need a little bit more for logistic regression. But of course, as I said, it's a double-edged sword. So logistic regression makes lesser number of assumptions, or weaker assumption. Okay, it's only assuming something about the conditional probability of y given x. Okay, so if p of x given y is not Gaussian, then logistic regression is the better choice. Okay, it's better, it's more I guess efficient. Asymptotically just means when you have a lot of data. Okay, that's what it means. So it's more robust because it's making less assumptions, and so robust is the same thing as saying it's less sensitive to incorrect modeling assumptions, because you're only making some assumptions. Unless, so basically you kind of use stick with logistic regression if you want a linear model and you don't have any prior intuition about the data. But if you have, then you can be efficient by just doing GDA. So let's take a break here and resume in 12 minutes. Okay, so let's resume. We saw one example of a generative model, Gaussian discriminant analysis. It's generative because you are really setting up a generative story. What is the probability of being in one of the classes? And once you are in one of the classes, what is the probability of being? What is the probability of a feature vector, looking like something, right? Which happens to be a Gaussian distribution in that case. So next generative model that we're going to look at is naive-Bayes model. And so let's start with the motivation via an applications. Okay, so let's start with why one issue with GDA is, as somebody pointed out, every feature is assumed to be continuous and real valued. That's the minimum. I mean, in addition to that, we're also assuming that X is actually in each class is actually Gaussian. So the question is like, hey, what if let's go to the other extreme where each of our feature is discrete value. Okay, so we only have categorical features, and for that we'll kind of look at a canonical example, which is spam classifier. So spam, I think you might have seen several examples of spam classifier in this class and other classes. It's just an example. You can change it to something else. Okay, if you want to have a different running example. But let's stick with spam. So let's talk about feature representation of text, and this is something that we have done implicitly or even explicitly or overtly before. You can represent a text, a sequence of words via vector, right? So via vector, and how do we do that? We just create a vector with n coordinates. Okay. So each coordinate represents n coordinates. What are these n coordinates? This is the total number of different words in a dictionary. So n is the total number of words in a dictionary. Okay. Okay, and by dictionary I mean doesn't have to be all the words and which are not relevant to your application. You can always drop words which are not relevant to your application. And even if there are words in your application in your data set, you can always drop infrequent words or super frequent words, depends on your domain knowledge. Okay? So the vocabulary, you can determine the vocabulary, doesn't have to be exactly all the words in your input. Okay. Now, how do we represent this n-dimensional vector, which is exactly one hot encoded representation? So basically, think of each coordinate as a categorical feature, which is taking one of these. Each coordinate as a binary feature. Which is representing the presence or absence of a word. Okay? So, for example, the first coordinate is saying, hey, the word in this case A is present. And this coordinate is saying the word by is present. This last coordinate is saying the word dollar is present. Okay, and some words are not present. Okay, so we'll show you why naive seems quite simple, as you'll see in the next few slides, and some of you might have seen it before. But there's a reason why naive does better than some more more natural way of setting up this problem. Okay. Or a more natural way of setting up a generative model for this problem. So, let's start with a brief recall on how do we model a die. Okay? So a die, if it has 6 faces, let's say the die doesn't have to be equal probability outcomes on each of the face. If it has 6 faces, then generally you will have one parameter per phase, which is the probability of phase rolling up to phase 1 or phase 2 and so on. And they sum up to 1, right? So P1 to P6 sum up to 1. The number of parameters here is actually 6 minus 1. In general, if you have more faces, then whatever the number of faces minus 1, right? Now imagine we have this little n dimensional vector, binary vector, right? So how many such possible vectors are possible? Right? So the number of possible vectors is 2 to the power, let's say the number n is 50,000, then the number of x's which are possible is 2 to the power 50,000. Okay. Now you can imagine each of these vectors, having a corresponding probability value. Then you're really thinking of a probability mass function which needs to have 2 to the power 50,000 value. Okay. So basically, you can think of a 2 to the power 50,000 faces. Okay. So what I'm trying to say is basically that you have this vector, it's a binary vector. So really the support of this, if you think of each vector realization as a realization of a random variable or a random vector, then there's so many such vectors, to the power 50,000. And so you need to kind of have a number for each of these outcomes, right? That's what a probability mass function is. And that's just to describe the probability of one of these outcomes happening, right? So that's just for one task. Now, remember, we are actually trying to do classification. So we actually have to have probability of x given y equals spam, a bunch of such parameters, and probability of x given y equals regular, having a bunch of such parameters. Okay. Actually, you can ignore the under and subscript here for simplicity. It's basically some phi for the x vector and some phi for the x vector under both the classes. Okay. And so what is the total number of parameters? So for each class, under each class, we are saying, hey, I want to just find a PMF. Because I have to do about 50,000 values, realizations for random variables. Therefore, I'll have to the power 50,000 minus 1 is just for, because it's down to 1, times 2 plus an extra 1 because I also need to model the probability of class 1 versus probability of class 0. So it's just the count of, hey, how many are spam and how many are not spam, right? Remember, we did the same thing for Gaussian discriminant analysis as well. Okay. So any questions about this parameter counting exercise here? This is just to show that, if you naively think of, a very rich model like this, sorry, it's not a rich model. It's a model which is making minimal assumptions about the x, the feature vector, and because of that, it's actually having to pay a price in terms of the number of parameters to be learned. Okay, so which is exponential in the number of words to the power 50,000. Any questions here? Okay, so can we train this model? Well, we have a lot of data. Can we train this model? Well, the answer is, at least today's computers probably no, because to the power 50,000 is a huge number. Okay, so you can't compute it using your current machine. So the trick which naive-based model really relies on is a simple idea that we're gonna make an assumption. Okay, we're gonna assume that xj's, remember, xj's are these binary indicator random variables which, when strung together, create that 50,000 dimensional random vector. Each one of them are conditionally independent of the other given y. So only when y value is given, they are all unrelated to each other. Whether one of them flips to 1, the other one flips to 0, are unrelated to each other, as long as I tell you what y is. Okay, that's the assumption being made. I guess that's what I wrote here. So if I tell you whether y is equal to 1 or 0, whether this particular email is spam or not, then knowing whether or not the word buy appears in that email has no effect on whether the word or the symbol dollar appears or not. Okay. So basically, let's say buy is 1024th word and dollar is like 32,000 words. Then the assumption just means exactly like this. Right? The probability of x given y for the specific word, the binary random variable, is equal to probability of x given y and the second random variable. So this is how you would say something is conditionally independent. Basically, the right-hand side expression simplifies to the left-hand side expression. Maybe we should have written the other way, or in the other side, it's basically right-hand side expression drops the conditioned extra data. The extra data is not useful. So whatever 1024th random variable value it took, it doesn't have anything to do with what value the 32,768 random variable value to take, the value to take. So this, it's a crucial important difference is that is not equal to just independence between these random variables. Okay, so probability of x. So what I mean is the probability of x 1024th coordinate is not equal to probability of x 1024th given x 32,768. Okay. If this was true, then you would say that then these two random variables this x and the second x are independent. Okay. But we're not saying they're independent. Okay. In fact, if they're independent, then there's going to be a huge issue with this model. So the model is actually saying that condition the class they are independent. Unconditioned, they're not independent. Okay. So it's still retaining some strength about dependency between these words, It's just that they're conditional on being in one of the class or the other, they are independent. So conditional independence is it turns out it's a weaker assumption, and it's more realistic, relatively, it's all relative, more realistic assumption than independence for sure. It's, of course, it's an extra assumption. If you recall the previous slide when we said, hey, there's no assumption being made except for under each class it's a PMF, then that would be even less assumptions, but then you have a huge number of numbers to estimate. Here, because we're making conditional independence assumption, we will see in the next slide that the number of parameters to learn is much smaller. Okay. It's still been 100,000 plus, but it will be smaller for the 50,000 word example here. So any questions here? So what is conditional independence in effect? What is its influence on our distribution here? So let's really look at the joint distribution of the word binary or word random variables given the class. Okay, so I'm just looking at one version, one particular conditional probability. So this joint distribution between the words conditioned on a class, we know that this joint distribution conditioned on a class, we can always split it out. This is just a total of probability. The probability of x1 given y, probability of x2 given y, and x1, probability of x3 given y, x1, x2, and so on. Okay, so this is, you should be able to write this. So the way you would think about it is you can drop the condition on y and just expand it. Okay, so that will be very clear that this is, this is just factorization, there is no assumption. But in the second line, we're just saying that, hey, look at the second term, x2 given y and x1, there's no need for x1. So probability of x2 given y is just translated like this. So x3 given y and x1, x2 no matter anymore. X3 given y just translates like this, and so on. Okay, so this is the I guess this joint distribution between the x's given y splits across as the product of the probabilities of each individual x's given y. Okay, that's the conditional independence. Okay, and so that product representation is shown here. Okay, so this is just short form. You'll see in assignment number 5 also we kind of do this. Any questions here? Okay, so under that assumption, so even before, so actually the existence of each word is the result of Bernoulli graph. Remember, the x's are just indicators whether the word is present or not. So it's a Bernoulli random variable. Okay, so we need to prepare a basically coin with two-face coin, basically heads or tails for each coordinate, and each coordinate will have its own bias, and we'll flip each of those coins once, and so 50,000 trials. Okay. So for example, the modeling a single document, we need to do 50,000 coin flips. So the 50,000 numbers. Okay. So and whether you're in a spam class or the regular class, once you determine whether you're in one of these classes, and given these 50,000 numbers, probability of seeing some word, some collection of words is exactly given like this, right? So it's just, hey, probability of A was present, so let's take the parameter phi of A. Second word maybe was not present, then 1 minus the phi of that second word. Maybe Y was present, the phi of Y, and maybe the last word was not, last but one word was not present, so 1 minus phi, and last word was present, so it was phi. Okay, so I'm just expanding out like what is the value of a particular feature vector. And so in order to model the joint distribution between x and y, we have this, so we need to learn these p's per class. Okay, so we have two classes, so that's why we have a p1 for the class 1 as well as p1 for class 0. So under spam we will have a p, under regular we will have another p. Okay, and we'll, in addition to these two sets of numbers, we'll also need to learn the marginal probability of y itself, which is probability of spam and probability of not spam, or probability of regular. Okay. So given this accounting, that the number of parameters is 2 times 50,000 plus 1, right? So plus 1 is for the second bullet point, and 2 times 50,000 is for these fees value. So you can actually also do 2 times 50,000 minus 1, because if I tell you all these fees, one of the last fee is not needed because they have to sum up to 1, right? So if you have k classes in general, then the number of parameters is, instead of 2, there'll be k times n, or n minus 1, if you really want to be, correct there. And then instead of +1, there'll be k minus 1. Okay, so if you have 2 classes, then an extra 1 parameter. If there are 10 classes, there'll be extra 9 parameters. So why are we counting these parameters? Just to contrast with the previous setting, we did not make the naive Bayes assumption. It would have been k times 2 to the power n, okay, or 2 to the power n minus 1. Okay, that would be too many parameters. 2 to the power n, when n is 50,000, is like a huge number. Okay. So here you have a 100,000 and 100,001 number of parameters to learn, which is still a lot for such a simple model, but much better than the previous situation. Any questions here? We're just accounting for parameters for this model. This is a generative model. As you can see, given this conditional probability of the features given the class, and given the class itself, you know the joint probability of the features and class, and so you can always compute the prediction. Okay, so we'll talk about it in the next slide. So probability of x given y, we just saw this product form. So what is this product form doing, right? So remember, x was for a given x, x1 will be 1 or 0, x2 will be 1 or 0, and so on. How would you compute? How do you say what is the probability of a given sequence, given collection of words, under a given under a class? It's just going to be probability of xj given y to the power xj. Okay? For the xj's which are 1, plus 1 minus xj times 1 minus the probability for the xj's which are 0. Okay, so sorry, when I said that, I just meant when xj's are 1, this term will remain. The xj's are not 1, then this term will remain. Okay, so for every xj, the generic term is this. Okay, so either xj is 1 or 0. If xj is 1, then only this term remains. When xj is 0, only this term remains. Okay, so I guess that's clear. We have done it several times. So joint probability is nothing but the marginal probability over y times the probability of x given y. Okay, so x given y, we just get it from before. That's the joint probability. And then the marginal probability of x itself, okay, is just the average out y, and so that's just this expression with an extra sum in the front. Okay, so why are we doing these steps? Is because ultimately we want to do classification, right? So far I've been only talking about the probability of x given y and all the details related to that. So as we saw in the previous slide as well here, so the parameters are this: per class you'll have 1 parameter per word. Okay? So under class 1 there will be 1 parameter, under class 0 there will be 1 parameter, and then finally 1 parameter for the class proportions themselves. And okay, so I'll talk about the prediction in just in a second. So to learn the parameters, we just did the exercise for multinomial or categorical situation at the beginning of this lecture. So so you can define the likelihood of the joint likelihood of the data and estimate the parameters separately. Okay, so estimate the parameters, this collection of parameters, this parameter, and this collection of parameters separately. Okay, so basically you have 2 multinomials and one binary Bernoulli random variable. So 2 multinomials and 1 Bernoulli. All of them will be estimated by just counting and normalizing. Okay. So for example, I mean, I think we saw this. Emily estimation is just 5 by 7, for example, for this Bernoulli. So this we can do this for the y parameter, so the class proportion parameter, and then the parameters for each word itself under each class will be again count. Okay, if you are in class 1, then how many examples were in class 1, and then among them, how many times did that word appear, basically. So it's just a counting and normalizing. So under span, how many times did this word appear? Then that will be the parameter for that word under span. Similarly, under regular, how many times did that word appear in proportion to the number of regular examples would be the parameter for that word under regular setting and under regular class. And then C, I just said, is exactly like this. Okay, this is the count. Any questions? Okay, so once we have this, then the estimation, again, when we saw GDA, Gaussian discriminant analysis, we already saw this. You just, and this is the same thing we were doing for even discriminative setting. Okay, so which is the probability of y is equal to 1 given x should be greater than probability of y is equal to 0 given x. So this is where, I mean, if you remember from assignment 1, actually, we were picking a threshold 0.5. Okay, so for example, we were doing regression with, so we were doing classification via regression, and we just said, hey, why don't we just pick a threshold of 0.5? And in assignment 3, for example, we spent a lot of time trying to pick thresholds using graph curves, for example, right? So here the threshold is implicitly 0.5 because it's binary situation. If you're saying class 1 is probability 0.6, then clearly class 2 is probability 0.4 because they have to count to 1, right? So in that sense, if you're just looking at the probability of one of the classes, if it crosses the threshold 0.5, then it's class 1. If it's less than 0.5, it's class 0. It's the same equivalent thing to say. But the whole point of graph curve is that we don't care about just accuracy, not just being in that. We don't just care about accuracy, we care about confusion, and that's why the thresholds can be not just 0.5. So in general, for k classes, it's going to look like this. Argmax over, you'll have k different proportions. It's going to be again a probability mass function over y values or k values, and then whichever is the maximum among those k values will be the class. And so the general expression is this. Okay, so this expression actually is the, I guess, the final expression for naive Bayes because it uses all the parameters that we've learned so far. Okay, so probability of y is equal to k being in the k class, given that feature vector, given that 0, 1 vector is, hey, pick up, there are going to be n such random variables, remember? So j is equal to 1 to n of the the probability of, see, I think there should be a product. Yeah, I'm getting blanking on whether it should be a product or a sum here. If you know, just let me know. But basically, you are picking up the parameters corresponding to the case class and using them. Actually, it should be product, unless I'm mistaken here. But basically, all the parameters that you learned here, these TJs, are going to be factors here, and then the last term is also one of the P's that you learned. Okay. So anyway, so if you want to do this comparison, you need one each side, and that can be computed using the parameters. Any questions about this part? Okay. So now let's look at a slight variation. This is also part of your assignment question 2, I think, or question 1. So basically, the variation is, instead of looking at indicator, which is the presence or absence of a word, we're going to look at each coordinate being the number of times the word appears in that location. Number of times the word appears in the input. Okay. So slightly different. I mean, it's the same length vector. It's just that instead of each coordinate being a Bernoulli, now each coordinate is a categorical random variable. Okay. Sorry, each coordinate is going to be a each coordinate is going to be a count, and so the whole vector is a realization from a multinomial distribution. Okay, so it's like, yeah, so each vector is a realization from a multinomial distribution. Yeah, so the difference is like 10, 7, 3 versus 1, 1, 1, 1. So yeah, so we were previously just doing presence and absence of the word. Now we are doing we are actually modeling the frequency of the word. So instead of think of a die, so we had a die, and each location we are saying each of the die, each time we throw a die with n cases, we have to toss little l number of times. So basically, okay, let me give the example. So if you have a document with 50,000 words, then you need to look at throwing the first. So if you observe a particular sequence, okay, particular sequence of words, a particular input, then you need to take into account that the first word appeared 10 times, the second word appeared 7 times, third word appeared 3 times, and so on, out of the total number of words that have out of total number of words in your vocabulary. Okay, so let me explain it a little bit better. So this coefficient here is very similar to the coefficient that we saw when we're doing parameter estimation. In the parameter estimation, we actually expanded out this A choose B expression, and so that we had an n factorial divided by count of xi factorial. It's the same thing over here. Okay, these are just numbers, kind of just numbers that come from factorial divided by n minus r factorial and r factorial type of expression. But what's new is basically this to the power 10 to the power 7 and so on. Okay. So what changes basically the Jordan distribution again has the same parameters, so the number of parameters don't change. So it's still P1 to P 49,000 or P 50,000 for the class 1, and P1 to P 49,000 or whatever 50,000 for class 0, and in addition to that, probability of class itself, probability of y equals 7 or not. So the number of parameters is 2 times 50,000 minus 1 plus 1. So I think previously we didn't include this minus 1, but we have k classes, then it's going to be k times n minus 1 plus k minus 1. So this is basically the same formula as before. Yeah, and it doesn't have to be, we just saw, I mean, if you have k classes, it just expands to k. So there is a multiplicative factor of every time you have, like, instead of spam versus regular, if you had category 1 versus category 2 versus category 3, okay, or let's say you did sentiment analysis, like you had like 10 sentiments to take into account. Each extra sentiment is basically asking you to estimate the vocabulary number of parameters. Okay, so it seems like every time you have to have finer level of sentiment, then you're basically expanding the number of parameters you need by the vocabulary size. Okay, which seems a lot, but we just saw that it's not that much compared to not assuming conditional independence. Okay? So again, the expressions for the conditional probability of x given y, joint probability of x given y, and the marginal are very similar. The only difference is the raised to the power the number of times that word appears. So previously, the probability of x given y. Okay, so this I guess is better expression than this example here. So probability of x given y is this coefficient here. So which is the total number of it's the total number of it's the sum of the x vector. Okay, so x vector has 10, 7, and 3 in my running example. So the sum of all that, which I guess is 20, would be the numerator here, and then L1 factorial will be like 10 factorial, L2 factorial will be like 7 factorial, and so on. Okay, and it's just saying that hey, those 3 words, probability of that word to the power how many times it appeared. Okay, it's a little bit different expression than before. Remember, before we had a probability of x given y, which was presence of a word, is Bernoulli, and the absence of a word, which is 1 minus p. So there were like 50,000 terms here. Here, because of the multinomial assumption, only the words that are present and have some count, so basically count 1, 2, or 3, or 4, only their terms will be present here. Yeah, because to the power Lj, so Lj will be 0 for many of the words that are not present. So if Lj is 0, then p to the power whatever Lj will be 0. So that p will not be there. Okay, so that's a difference, and you will explore this difference in the assignment. Okay, so in fact, one of the questions in the assignment is about what's the difference. Okay, and the joint distribution, I guess you just plug in this expression here in the next couple of lines. So the model parameters are exactly the same as before, except the way they use is different. So Pj given y is equal to 1 and Pj given y is equal to 0, as well as P of y is equal to 1. Okay, so the estimation will be slightly different. I don't want to, there seems to be a lot of summations going on here, but the intuition is exactly as what I mentioned a few minutes ago. For Bernoulli naive Bayes model, the class conditional probability, the class proportions parameter is just going to be number of spans divided by total examples, and or number of regulars divided by total examples. Per class, the probability of a word is just subset data frame or subset the examples to the ones which are spam or regular. Under them, how many times did you see that word? Okay, presence or absence of that word. It's just a proportion frequency count here. Unlike that, the count for this is just completely again yeah. So now what's going to happen is you will have an extra LJ, which is a data point for your data, right? So there will be a weighting of this LJ in your proportion computation. Okay. So this Py will be the same as before, but Pj of y under y is equal to 1, let's say the class 1, is just going to be the number of times. So it's just the number of examples which are, let's say, regular, and then out of the regular ones, how many times did this word appear? And then whenever you're doing that, you have to also divide by, for that example, how many times any of them did appear. Okay. So there's a weighted averaging going on. So Lj and L factor in the numerator denominator. Okay, so that was a lot of details on the computation of these estimates. But these estimates ratios that you're seeing, you get those ratios exactly by doing the parameter estimation procedure that we did at the beginning of the class. We did it for a general multinomial situation, but we are actually doing that per class here, okay? And it's just a subroutine for this naive-Bayes model. So let me just summarize, summarize what we discussed so far. Bernoulli versus multinomial naive-Bayes. Both are bag of words assumptions. So the X feature vector, so there's going to be one coordinate per word. Bag of words assumption just means that the word ordering doesn't matter. So you just kind of like from the X vector representation, you can't construct back the actual sequence of words. Both are using one-hot encoding. Of course, the multinomial version is actually taking into account the count of the word at each location. So basically, I guess the difference, as it says here, is binary vector per text. So it makes sense for short documents. So this, I guess, is a more empirical observation. It may or may not make sense for different applications, but multinomial, it's integer vector per text or per word. Okay. So of course, if you want to have integers and counting up, then of course you want to work with potentially longer documents. I guess that difference basically manifests in Bernoulli probability of D given the class could be could be 1, as D always exists in maybe both, but irrespective of which class you are in, D always exists. Whereas in multinomial, probability of D given Y could be, again, could be high, but it could be, it's a proportion, it's a number. Remember, this is a Bernoulli. It's like probability of D being present or not under the class. Okay, that could be high number. But in the multinomial case, probability of D given Y is a coordinate of a multinomial expression. Okay, so that's why it's like among all words, what is the proportion of words that D takes is this number. Okay, so there's a difference because of the counting. I think this is last slide. Yeah. So what I'll do is summarize now, but we kind of a little bit behind. We have in terms of assignment, for example. So we have in the assignment there is hidden Markov models, and there's also k-means and PCA. So those are the 3 topics to cover. I don't want to start hidden Markov models now because it'll then split over 2 lectures. So we'll try to cover as much of these 3 topics next lecture, so that you have 1 more week for the assignment 5. But to cover what we did today, we started with just differences between generative versus discriminative models. It's not super, it's not a critical thing that you have to use generative models, you have to use discriminative models. It's just that when you have domain knowledge, as you see with GDA or naive-Bayes, sometimes it's advantageous to actually take that into account. Okay? And you can think of these 2 as just 1 or 2 examples of this whole class of generative models. As I said, you can also look at probabilistic graphical models as a rich literature on that, very useful in many big industries, maybe not tech, but automotive, finance, healthcare, and so on. So we saw generative versus restricted model distinction. Then we briefly looked at constraint optimization via the definition of a Lagrangian. We just saw a necessary condition for a solution to be potentially an optima, and you have to check more so that it's actually a maximizer or minimizer. And then we look at Gaussian discriminant analysis, both the linear version as well as the quadratic version. Linear and quadratic. So linear version is comparable to logistic regression. Quadratic version gives you nonlinear decision boundaries. And then we looked at naive Bayes. Although naive Bayes at the end of the day, if it's not motivated this way, it seems very simple model. But you can imagine that every time you have for binary case, and the number of words really influence how many parameters there are. And so the number of parameters could be much larger than, for example, a typical linear regression or logistic regression model that we're building. It can be quite large. And so there are two variations that we saw: the Bernoulli version and the multinomial version. Each has its own advantages and disadvantages. Okay. Yeah. So I think we can end a little bit early. And if you have any questions, you can ask. I know there are no questions there.